So we have a sprinter who runs with a constant acceleration of k, so speeding up throughout the race, and passes posts A, B, C, and D, such that the distance from A to B is 36, B to C is 36, and C to D is 36 also. They're all equal sections. He takes different times to travel between the posts. Obviously, as he's accelerating, his speed is increasing. From A to B is 3 seconds, and from B to C is 2 seconds. Our job is going to find the time taken to travel from C to D. And so a common sense answer is that it's obviously going to be less than 2 seconds. If he's speeding up as the race goes on and he's traveling equal intervals each time, well then obviously the distance from C to D is the same as B to C, but he's just going to cover it in a quicker time, so less than 2 seconds. So the problem with a question like this is if we decide to allocate the letter U for his initial speed at point A, we can't then go and use U again for point B. And so in sectioning off the journey, if we decide to go, let's say from A to B, U is the variable, and that's fine, we can use the letter U, but we cannot use U for the section B to C, or indeed for the section C to D. He's no longer traveling at that speed of U. He's increased his speed, and so we can only use U if we decide to start the question in A, and that's exactly what we're going to do. We're going to take the section of the journey from A to B, where his initial speed was U and his initial acceleration was A, and that turns out to be his acceleration throughout the race. And then we're going to take the section of the journey from A to C, which is a different section of the journey, but by starting again at A, we can say that his initial speed is still U and his acceleration is A. Now note, U is not equal to 0 in this question. He started the race sometime before he got to A, so he didn't start the race at a speed of 0 at point A. Okay, so what are we going to do? Well, let's go and write an expression for the distance A to B. So U is U, A is A, the time taken to go from A to B is 3, and the distance travelled is 36. And if we sub them into our formula, S equals UT plus a half AT squared, and then tidy up that formula, we have equation 1. 36 equals 3U plus 4.5A, and I'm just going to label that equation 1. Like I said, we can't then go and take the distance from B to C because we'd have to introduce a new variable for the initial velocity at B. And we don't want to do that. We don't want to call that V, or we don't want to call it any other letter. So what we're going to do is we're going to take the section of the journey from A to C, which took 5 seconds and is a total distance of 72 meters. And again, we can keep U as U and A as A, and those are the variables we're trying to solve for. So subbing them into the formula, we get 72 is equal to U times 5 plus a half A on 5 squared, and then tidying that up we have 5U plus 12.5A is equal to 72, and I'm going to call that equation 2. So to solve for U and A, we have a simple simultaneous equation. I'm going to multiply equation 2 by 3 and equation 1 by minus 5 so that I can cancel the U's in this question. So multiplying the top line by 3, I get 15U plus 37.5A equals 216, and multiplying the bottom line, which is equation 1, by minus 5, I get minus 15U minus 22.5A equals minus 180. I'm going to draw a line underneath, I'm going to cancel the U's. Adding down the rest, I have that 37.5A minus 22.5A is 15A, and 216 minus 180 is 36. Dividing both sides by 15, I get that A is equal to 2.4 meters per second squared. And that's the acceleration throughout the race. For every second that passes, this runner is increasing his speed by an additional 2.4 meters. To solve for U, I'm just going to sub this value of A back into either equation 1 or equation 2. So I'm going to choose equation 1, and I get 3U plus 4.5 times 2.4, our new acceleration, is equal to 36. So 3U plus 10.8 is 36, subtract the 10.8 from both sides, and 3U is equal to 25.2. Divide both sides by 3, and we get that U is equal to 8.4 meters per second. The final part of the question, we've solved for U and A. We want to find the time taken to go from C to D. Again, we can't just take that section of the journey, as U is not equal to 8.4 here. U is equal to 8.4 at the start of the race. So what I'm going to do is I'm going to find the total time taken to travel from A to D. That way I can start again at A and use U equal 8.4 and a is equal to 2.4. So what we're going to do is we're going to again use the s equals ut plus a half at squared formula. U is 8.4, a is 2.4, t is what we're trying to solve for, the total time taken to travel from a to d, and s is equal to 108. When we sub those in and tidy it up, we're left with a quadratic equation, 1.2 t squared plus 8.4t minus 108 equals 0. At this stage, I could try and factorize it, but I'm probably better off just straight away going into the minus b formula. That will give me two solutions. One of the solutions is negative. I discount that because we're looking for a time. And the other solution turns out to be 6.6 seconds. Now remember, that's the time taken to travel from A to D, not the time taken to travel from C to D, which is what we're looking for. So from the 6.6, I'm going to subtract the 3 seconds and the 2 seconds, so a total of 5 seconds. And I'm left with the time taken to travel from C to D is 1.6 seconds. So called common initial velocity questions because we want to go back to A each time to start sections of the journey so that we can use this common initial velocity U.